So the first thing to talk about with respect to VSEPR theory are the number of electron groups that we can have and the electron group geometry that results. The electron group geometry is the arrangement of all of the electron groups around the central atom. When we consider the electron group geometry, the identity of the groups don't matter. As we go on a little later to the shape of the molecule, over here in this column, what you will see is that the identity of the groups is going to matter at that point. But first, as we discuss the electron group geometries in this column, it's simply based on the number of electron groups. So in a case like carbon dioxide, like you see here, we have two electron groups around the carbon, which gives rise to a linear electron group geometry. In the case of boron trifluoride, we have three electron groups around a central atom, which gives rise to a trigonal planar electron group geometry. In the case of methane, CH4, we have four electron groups around a central atom, which gives rise to a tetrahedral electron group geometry. If we have five electron groups around a central atom, like in the case of phosphorus pentachloride, that gives rise to a trigonal bipyramid electron group geometry. Six electron groups around a central atom, like sulfur hexafluoride, will give rise to an octahedral electron group geometry. And once we identify our five basic electron group geometries, we can further identify the shape of the molecule based on the identity of those electron groups. And in order to do this, we need to differentiate whether our central atom is going to have bonding groups, which are going to be single bonds, double bonds, or triple bonds. A single bond is one bonding group, a double bond is one bonding group, a triple bond is one bonding group. And we're going to compare the number of bonding groups to the number of lone pairs that our central atom will have, which we see here. In any case where the number of electron groups is equal to the number of bonding groups, the electron group geometry and the shape of the molecule will always be identical. So in the case of methane, we have four electron groups. That gives rise to a tetrahedral electron group geometry. All of those electron groups are bonding groups. None of them are lone pairs, and that means that the shape of the molecule or the molecular geometry will also be tetrahedral. At our central atom, we'll have a bond angle of 109.5 degrees in that tetrahedral structure to keep all four of our electron groups as far away as possible. In the case of ammonia, when we look at the nitrogen, we see that we have four electron groups, and we know that that means we have a tetrahedral electron group geometry. But when we look at the identity of the electron groups, we see that three of them are bonding and one is a lone pair. That means that the electron group geometry and the shape of the molecule or the molecular geometry will not be the same in this case. In any case where I have three bonding groups and one lone pair, that gives rise to a trigonal pyramid shape of my molecule. In this structure, my bond angles are going to be 107 degrees. They're going to be a little bit smaller from my 109.5 degree bond angles that I saw in the tetrahedron. That's because my lone pair takes up more space and it's going to force my hydrogen, nitrogen, hydrogen bond angles to be a little bit smaller. In the case of water, when we look at the oxygen, we see four electron groups, and we know that means a tetrahedral electron group geometry. In this case, we have two bonding groups and two lone pairs, and that combination is going to give rise to a shape of the molecule, which we identify as bent. In the molecule of water, we have two lone pairs, and our lone pairs are going to be a little bit bigger groups around that central atom. They're going to occupy more space, and they're going to force that hydrogen-oxygen-hydrogen bond angle to be a little bit smaller and be about 104.5 degrees. Now, when we look at the three cases that we have for tetrahedral electron group geometries, the bond angle of 109.5 degrees in that tetrahedral structure is a very important bond angle that you know. When it comes to the bond angles for our combinations that we see for ammonia and water, the trend for the bond angle is important. That means that you must understand that a lone pair present in your structure will occupy more space, create a greater repulsion between itself and the neighboring groups, forcing the other electron groups to be closer together, compressing that bond angle. So that if I asked you a question to compare the bond angle in something like methane, ammonia, and water, you should be able to tell me which bond angle is the largest or which bond angle is the smallest based on what you know about the impact of a lone pair on the bond angles in our structures. Our next electron group geometry was trigonal planar. We saw that for boron trifluoride where we had 3 electron groups around the central atom. In a case where we have 3 electron groups that are all bonding groups, the shape of the molecule will also be trigonal planar. The bond angle that we see at the central atom will be 120 degrees. In the case of sulfur dioxide, SO2, we see that we also have 3 bonding groups. We know that that means we have a trigonal planar electron group geometry, but with the identity of the groups being 2 bonding groups and 1 lone pair, that means that our electron group geometry and molecular geometry will not be identical. In this case, we also identify the molecular geometry to be bent. The presence of 2 electron groups around that central atom and 1 lone pair means we'll ignore that position of the lone pair, focus on where the atoms are, and that gives us a structure that overall looks pretty similar to what we saw for water and we also classify as bent. In the case of carbon dioxide, when we have 2 groups around the central atom, there's no other combinations for molecular geometries other than the case where the central atom has 2 bonding groups and we have the linear electron group geometry and linear molecular geometry with 180-degree bond angles. On the back side of your handout, you see all of our structures where we have expanded octets. And there's 4 different molecular geometries that we can have within the classification of our trigonal bipyramid electron group geometry. In the case of phosphorus pentachloride, we see that we have 5 electron groups. All electron groups are bonding groups, so the molecular geometry and the electron group geometry are both trigonal bipyramid. Our equatorial groups will see bond angles of 120 degrees. Our axial groups will see bond angles of 90 degrees in that structure. If we look at sulfur tetrafluoride, we have 5 bonding groups at the central atom, a trigonal bipyramid electron group geometry, but the identity of those groups are that 4 are bonding and 1 is a lone pair. That means that we're going to identify the shape of the molecule differently, and in this case, 4 bonding groups and 1 lone pair gives rise to a molecular geometry that we call seesaw. We'll see a little bit of a compression in our bond angles as a result of the lone pair. In the case of bromine trifluoride, we have 5 electron groups around the central atom. 3 of the groups are bonding groups, 2 of the groups are lone pairs. What we know about our trigonal bipyramid electron group geometry is that the lone pairs are going to be sitting in the equatorial positions such that they have more space. So that if I ignore the 2 equatorial positions and I focus on the 2 axial positions and the 3rd equatorial position, I end up with a molecular geometry that I identify as T-shaped. In the case of xenon difluoride, I have 5 electron groups at my central atom and a trigonal bipyramid electron group geometry. 2 of the groups are bonding and 3 of the groups are lone pairs, and that combination gives rise to a linear molecular geometry. In this case, my 3 lone pairs are occupying the 3 equatorial positions in the structure, leaving my fluorines to be at the axial positions in the structure. My lone pairs are bigger groups, therefore they will sit in those equatorial positions so as to give themselves a little bit more space and minimize the repulsions between their neighbors. The bond angles for the bonding groups in this structure is 180 degrees. When I have 6 electron groups around a central atom, that gives rise to an octahedral electron group geometry. And when the identity of all of those groups is that they are bonding groups, I also have an octahedral molecular geometry. Throughout that structure, I have bond angles of 90 degrees. For bromine pentafluoride, I have 6 electron groups around my central atom, giving me an octahedral electron group geometry. And as I look at the Lewis structure, I know that I have 5 bonding groups and 1 lone pair. That gives rise to overall a square pyramid molecular geometry, where because all of the positions in my octahedral structure are equivalent to start, that lone pair can go anywhere. And so with one lone pair present in the structure, my overall molecular geometry will now be that of a square pyramid. For xenon tetrafluoride, I have an electron group geometry based on my 6 electron groups that are present, and it's an octahedral electron group geometry. The identity of the groups are that 4 of them are bonding and 2 are lone pairs. And in that specific combination, the molecular geometry that will result is a square planar structure. The first lone pair in the octahedral structure could go anywhere, but the second lone pair is going to go exactly opposite that in my structure.